Dear all, welcome to this video on proofs. So in this video I decided to connect philosophy and pure mathematics. As some of you may know, in pure mathematics we have a lot of logical reasoning that is tied down to philosophy. Back then in ancient Greek, when a lot of philosophers came up with ways, especially Aristotle, to find the truth, find statements, arguments to make logical conclusions. We have those methods in mathematics as well. We derive them from philosophy, all the way back then from ancient Greece. So in this video, I want to go over some proof techniques and how they relate to philosophy, and some readings I covered from a course I'm taking in philosophy to relate that to pure mathematics. Thank you all in advance, and I hope you enjoy this video. So I want to start with direct proof. So direct proof is one of the methods we use in pure mathematics to prove a statement. Okay, it can be a very simple statement, as we will be starting with an exercise on direct proof. But before that, I want to give a definition in my own words. In mathematics, the process follows for direct proof. If P is true, if P, then Q. Okay, if P, then Q, which means P is implying Q. And from the truth table, we know that if P is false, Q will be true, because the truth table is shown as if true implies true is true, true implies false is false, false implies true is true, and false implies false is true. This is a very interesting topic about truth table, and I think in the readings we do have that truth table, so I'm not gonna go so deep into that. But for direct proof, the idea is that we know that the only way we can make the statement false is when the antecedent, the assumption, is true and the consequent is false. So true implies false, and that will be a false statement from the truth table. Therefore, because of this, the direct proof builds on that and saying, hey, why don't we start with the antecedent being true and see what happens. Okay, so basically that's what we do. We assume that P is true, and then we try to mathematically show that Q cannot be false. Okay, so that's the method we use with direct proof. But as you can observe from this little presentation, there are many proof techniques in mathematics. So sometimes direct proof will not be the most convenient one. Sometimes it might not be possible to use direct proof, because the idea is depending on showing that Q cannot be false, assuming the antecedent is true. So if I can show that Q, the consequent, cannot be false, that would prove the statement using direct proof. Here's a very classical example. Anyone who will be taking Math 200 or 250 would be familiar with this one. The statement is, if n is even, if n is an even number, even numbers mean they can be divided by 2, then n squared is even. That's the statement. So first of all, analyze this statement as P and Q. Okay, so the initial antecedent n is even is our P. You can call it whatever variable you want, it doesn't really matter, but just for the sake of argument I would call it P. And then n squared is even. That if and then will be a sign that we understand this is an implication statement. So n squared is even means that this will be our consequent, and I will be calling that Q. So direct proof starts with this, assuming P is true, and assuming the antecedent is true. Okay, we are trying to show that the consequent cannot be false, assuming that the antecedent is true. So assume n is even. Assume n is even, okay? Now, then by the definition, now we are using definitions because definitions, as philosophy emphasizes on definitions in mathematics, definitions is very important with proofs and everything because we want to be exact with what we are trying to do here. So by the definition of even numbers, there exists an integer k such that n is 2k. Well, that is true. That's what the even numbers mean. If n is an even number, then it is divisible by 2. So k being an integer multiplied by 2 means that n is a number divisible by 2. So that's good. That's what we have in our hand right now. And we assume that n is even. Now we will be working with now trying to square both sides. Now what happens if we square it? Well, we're trying to get n squared basically to show n squared from using k. Okay, so we are kind of substituting 2k for n. And this means that n squared is 4k. Well, 4k squared. So 4k squared should be automatically telling you that this is a number divisible by 2 because 4 is divisible by 2. If 4 is divisible by 2, then 4k squared is divisible by 2. But you have to always go very, very back into the definition. You want to be very exact. You cannot just say 4 is divisible by 2, therefore we have to go with the definition. That's another process. So we're going to say that since k is an integer we defined previously, 2 times 2k squared, we are just going to write that differently than 4k squared, is also an even number by the definition of even number because 2 times 2k squared, k was an integer, k squared is an integer as well. An integer times an integer is another integer, so 2 times an integer is an even number. That's what the definition of even numbers mean. And this proves that n squared must be an even number. This just proves it. We have shown that it is not an odd number. Okay, so the consequent cannot be false, assuming that the antecedent is true. Therefore, this is a good proof using direct proof for this example. Now let's work on proof by contradiction. Proof by contradiction is an amazing way we can prove a statement in mathematics. Well, what we do is, from the name of its technique, it is contradiction. We're trying to show a contradiction. So what we're trying to do is we're going to say that the initial antecedent is true and the consequent is false, which means true implies false, which is false. Okay, so we are going with that direction. You might say, hey, why are we doing this? Why are we trying to show that this is false if we are trying to prove the statement itself? Well, here's the thing. If the statement is true, it's actually true, we will not be able to do that. When we do that, we're going to come with a contradiction of something that doesn't make sense, something that's impossible or mathematically incorrect. Okay, maybe something like 1 equals 2. Okay, and at that point you're gonna say, hey, I just worked with that false possibility and that was not true. Mathematically we proved that the false possibility is not true, therefore then the other possibilities are always going to be true. So that's opposite of what we did, so basically it has to be true. So we go backwards when we start with that false conclusion, then the proof shows itself, we result in a contradiction, and this contradiction can be with the antecedent, and since we assume that the consequent was false and the assumption was true, resulted in a contradiction, this proves that the statement is true. Now let's work with an example to further understand this idea. Proof by contradiction. Now we want to prove the same thing. I wanted to use the same example so it will be much more easier to follow intuitively. If n is an even number, then n squared is even. Okay, we just proved that using direct proof. How can I use contradiction to prove this? Well, contradiction can be, we want to use a false possibility, right? So I'm going to say, hey, assume n is even and n squared is odd. Okay, that's accepting the antecedent and rejecting the consequent. Since n is even by the definition, we're always going to go with definitions the moment we make assumptions, because definitions are basically there to show what's going on and prove it. So by the definition of even numbers, n is equal to 2k for some integer value k. N squared is 4k squared, as we discussed, which is 2 times 2k squared. Well, 2 times 2k squared is an even number. And by the definition of even numbers, this contradicts the assumption that n is odd. This proves the consequent is not false, therefore it is proven. Well, yes, this is a very similar proof we did with the direct proof. You can say that, oh, isn't this the same? Well, not exactly. This is the same statement, so it does feel very similar proof-wise, but it is not exactly the same, because here what we did was, initially with direct proof, we just assume for the antecedent, but for contradiction, we assume the wrong one. We assume the false choice. We assume the antecedent and the consequent by together. And that's how we achieve the contradiction with the truth, that and for 2 times 2k squared is an even number is the truth, and the assumption was it's odd. So basically that's the contradiction here, and that's how we prove using contradiction. Now, proof by contrapositive. This is actually, I don't like to call this a proof. I mean, it is a proof, but what we do with contrapositive is we basically, as we have discussed previously in the class, we convert a statement. We say that, hey, P implies Q, okay? This is P, this is Q, P implies Q. Well, why don't we do this? Not Q, or negation is not. Negation of Q implies negation of P. Well, the truth table of the negation of Q implies negation of P is the same as P implies Q. So, well, mathematicians said, hey, sometimes it's much better off to use this representation, this expression of P implies Q for some theorems, that it will make it much more easier to work on. Sometimes the direct proof or the proof by the contradiction would work much better with the other way around. And since they have the same truth value, we can just rewrite that expression and just work with that, just playing around with all of the math and just showing that the contrapositive is true or false, whatever we are trying to do there, and showing that it is true, it will mean that the original statement is true itself, because they share the same truth value. If the contrapositive is false, the original statement is false. If the contrapositive is true, the original statement must be true. Here is an example with proof by contrapositive. It's the same idea. It's the same statement. If n is even, then n squared is even. Well, before I tell you, I would like to invite you to try this on your own, because I think it's very exciting to try to prove things. So, well, on top of my head, I can just say that why don't we assume that n squared is odd, and if n squared is odd, then n is odd as well. That's the contrapositive of the initial statement. If n is even, then n squared is even. Well, before we jump into the proof, think about this. If n is even, then n squared is even, which makes sense, okay? How about if n squared is odd, then n is even. N is odd, I'm sorry. How about that? If n squared is odd, then n is odd as well. Well, thinking about that, that does make sense. Try an odd number. For example, odd square could be 9. Then n would be even. What is 9 the square of? It's 3. So we're going to have 9 and 3, which are both odd numbers. That does make sense. So intuitively, you can go with that, but don't give examples when you want to do proofs, because you're not proving anything by giving me an example. You can give me 1,000 examples, but that's not going to be a proof. I need to know for sure that that would work for every single possibility. So that's not, examples are not good enough. So proof by contrapositive. Well, we're assuming that n squared is odd, then n is odd, which is the same truth value. Assume that n squared is odd and n is even. Now I jump to direct proof because I know that the statements are going to have the same truth value, so I can just use any technique I want to prove that if n squared is odd, then n is odd as well. So I just wanted to use direct proof. Okay, so we assume that, I'm sorry, this is actually proof by contradiction. Assume that n squared is odd and n is even. We assumed for both the consequent and the antecedent. By definition of even numbers, n equals 2k, where a k is an integer. N squared equals 2 times 2k squared. N squared is even, but we assumed that it was odd. That is contradiction. Therefore, and if n squared is odd and n is even, is basically a contradiction. And because it was a contradiction, the original statement, if n squared is odd, then n is odd, is true. And because that was a contrapositive, if n is even, then n squared is even, is also true. Okay, now let's think about this. We said that using the contrapositive, if n squared is odd, then n is odd. And assuming that, we then use proof by contradiction. So we first use contrapositive and contradiction. Well, notice what we got there compared to the original statement. If n squared is odd, then n is even. Now I want to work with some quotes from the textbook I really liked. So one quote I found from the textbook is, "Scientific method is the most powerful and successful form of knowing that has been employed. It is adventurous, curious, rigorously logical, and inspirational. It is even possible to be artistic about scientific discoveries." And I love this artistic word because math is just about being artistic. And the best part about science is that anyone can do it, which I totally agree. Science can look difficult because there's a lot of jargon involved and a lot of math. But even for the most complicated quantum physics and the most far-reached astronomy follows the same method in principle as a primary school's project in which you played with magnets or built a model volcano. So I love this quote because it does show you that, the scientific method is not discriminatory. Anyone can do it. Anyone can do it. It is very simple. Doing quantum physics and doing your elementary school project involves the same logical steps which humans came up with to make statements, conclusions, and understandings from all the way from ancient Greece. And this is something I love about this class, that we are working with really primal ways of thinking, but they are the ideas that make every complex thought possible today. So I love how the fact that from the simplest to the most complex observations all follow the same method. That's what is implied from my understanding of this text. So that's very nice from that M2. For M3, I found that there are two big ways that statements can be ambiguous. They can be using improper semantics or improper syntax. A semantic problem is one where you are running off of the meanings and word choices you have made or are using, and a syntactic problem is one where you are not phrasing or organizing your thoughts in a clear fashion. The goal with any writing is to make sure that your intended message is properly received. The best way to do this is to speak clearly, directly, using the most precise words and grammar that you can. So I like this quote because it relates to mathematics proofs using, exact definitions, clear words, things that make sense. You always want to be exact and clear. You don't want to leave any ambiguity in your proof. So that's very, I agreed, and I think it's really relevant to this discussion. And another quote from M3 is, in a conditional statement, if then two conditions are given, a necessary and sufficient condition. Sufficient conditions is a sufficient condition. A is a sufficient condition for B whenever A is all that is needed to make B true, or whenever the occurrence of A is all that is needed for the occurrence of B. Necessary conditions are just the same thing, implication, but the other direction. So B is a necessary condition for A whenever A cannot occur without B also occurring. Or whenever A cannot be true, B also being true. Or you can just replace that by, if B, then A. Just play around with it. Just do the converse of that. And that will be, so in all the cases above, the consequence is a necessary condition. So relevancy to proofs, I think these readings offers us very good insight on the importance of definitions, understanding necessary, sufficient, and both necessary and sufficient conditions that make proofs and logic so much more easier to follow and understand. Finally, I took this quote from M7. Modus ponens is the Latin term for affirmative mode. We can also call it affirming the antecedent, because one of its premises affirms that the antecedent of the conditional is true. It is a valid form based on the concept of sufficient condition. If P is sufficient condition of Q, then and Q is P is true, then Q must be true. Yeah, so this is basically what I find to understand is it's really connecting to direct proof. Just like we did in direct proof, we like to call the antecedent true in showing that the consequence cannot be false. And this is how we construct our proofs using direct proof, which is very, very similar. And logically, it is true that the only way the conclusion is false is by assuming that the assumption is true, and this logic can apply in many areas in life. So before I finish this presentation, I'd like to ask some questions that was kind of mentioned in this presentation. How do you think these proof techniques can be used in simple real-life scenarios? These proof methods can be used in everyday life whenever people reason carefully from evidence. Can you think of some examples? I invite you to think, first of all. Please pause this video and think about it. But I think a lot of the times, especially if you like to read Greek philosophy, ancient Greek philosophy from Socrates, like Plato, Aristotle, their work, you're gonna notice a lot of arguments, especially Plato when he's writing about Socrates. There, he's like a guy just walking on the street and talking, but he's like from the text you can always see a logical way of thinking, a logical path to follow. Sometimes not maybe that not logical, maybe not very objectively logical, but most of the times they're very good examples of it. So that's the thing so interesting about logic. It's very applicable for everyday life, and I just wanted to give you a little hint for this one. Consider this: if I do my homework, then I will pass. This is a statement. This is a premise. And how do you think I can use these proof techniques? Well, direct proof. Let's think about direct proof. Okay, assuming the initial antecedent is true, what will happen if I do my homework? Can I will not be passing be true? Well, technically yes. Technically yes. And this is also a way to give a counter example that this is not an entirely true statement, because I can do my homework and I might not be passing. But for the sake of the argument, we will assume that this class is only built on homeworks and no exams and no anything else, and as long as you put effort into your homework, you're gonna pass. Okay, that's a course. So let's do direct proof. If I do my homework, is it possible that I won't be passing? No, you will pass. So that's why direct proof is a good proof. We can prove that if I do my homework, then I will pass. How about contrapositive? If I don't pass, then I didn't do my homework. Yes. Well, if this course is again only built on homework and that's the only thing they're grading, well, yeah, if you didn't pass, it means you didn't do your homework. Okay? Which does share the same truth value as the original statement. And contradiction. Well, how can I do contradiction? If I do my homework, assume that's true, and I did not pass, it's true as well. So if I did my homework and then I won't pass, is that a true statement? We must now search for a contradiction. Well, yeah, there is a contradiction. I have to pass if I do my homework. Not passing doesn't make sense because I did my homework. Therefore, using proof by contradiction, this is true. So now, moving on, my next question is why is proving something so important? Well, on the right hand side, there is a very good movie called The Man Who Knew Infinity, and I urge everyone to at least see this movie. It's a very, very well designed movie and kind of historic. There is this young gentleman called Ramanujan from India who went to Oxford College. Actually, he didn't go, but he sent his theorems, mathematical theorems, to Harvey when he was in India, and Harvey analyzed them and saw very good potential. So he invited him to Oxford College to prove these theories. But one thing about Ramanujan is he never liked to prove it, and because he never most of his work were not proven, a lot of the times the scientific community wouldn't accept it because when you want to make big statements, big theorems like that, you have to be able to prove it. Because what if it doesn't work out? What if, especially for his work, he was working with prime numbers and partitions and the number of prime numbers, and using as a function how it will increase or decrease in a given interval. And well, it does seem obvious that he was suggesting that it will mostly predict more the actual number of primes, and it will actually be somewhere around his estimations. But what if not? What if a very big number comes up and in that interval it doesn't work out? So basically, the idea is it might not work out for everything because there are infinite amount of numbers that could be worked on. So Ramanujan, they gathered and tried to prove it basically, and this is why proving something in mathematics and philosophy is very important. One fun fact about Ramanujan is, I think there's I'm pretty sure there's one of his mathematical theorems about pi, the number pi, that is not entirely proven, but because his work was mostly other work was proven and Ramanujan was really well respected on that aspect of being right with his theorems, it is assumed to be true. Well, that's the only exception, and I think that's very interesting. So that's one fact about that. And finally, why do we need clear definitions to move forward with proofs? I kind of touched on this, especially also the textbook. Not having clear definitions or exact meanings will always alter your proof and create some flaws and inconsistencies, which is not, which will take you away from the objectivity. Finally, here are some references. I only use a textbook for this presentation. Thank you all for watching. Have a great day.